for the sense of belonging. Some people die before they fulfill their desires. Such a waste of existence. Spend our life searching for the sense of belonging. Some people die before they fulfill their desires. Such a waste of existence. Waste of existence.
The sun is shining and the anxious earth is rising. I'm so happy.
We spend our life searching for the sense of belonging. Some people die before they fulfill their desires. Such a waste of existence.
So that was the silent version. Now this is the version with the mic on. And so you decide which you like best. Okay. Oh, the mic is turned up. Look at that. We're all set here. Welcome to the Double Tribble channel. This is Double Tribble channel on Twitch. My name is Ron. I live in rural New Hampshire, and I'm surrounded by forests and wild animals and stuff. So sometimes I stream about that. I do IRL, but mostly I do science fiction. At least once a week, I'll do talk about a science fiction movie. But tonight we're doing live experiments, and this is kind of a follow-up. I did live experiments a couple weeks ago on radiation, and specifically I did it on visible radiation or radiation, electromagnetic radiation around the visible spectrum, close, up infrared, visible, and ultraviolet. And I did some experiments and they didn't work. they didn't work at all. In fact, let me. The experiments that I was doing was I was trying to, I was just doing a variety of different stuff. I would take lights and UV lights or whatever and shine them on different things, and just to see what was phosphorescence and what wasn't, and just a variety of stuff. One of the things that I did was I did an experiment where I don't have a spectrometer, but I wanted to see if stuff that the various lights are actually putting out the various wavelengths of stuff that they're supposed to, and what that would do to different things and stuff like that. And I took some glow in the dark material, and put different lights on that, and it turned out that the glow in the dark material worked really good with UVA, but not as good with the higher or lower frequencies, or higher or lower wavelengths. But one of the experiments I did was to see if I have a UVC lamp, and I wanted to see if it was actually putting out UVC. And one of the tests you can do to see if something is putting out UVC is to shine it onto the skin of a banana for a while, and if the banana turns dark in the area where you shine the light on, then that means that it had UVC in it, because UVA, visible light, and UVA and UVB don't do that, but UVC does do that. And I want to test that. I tried testing it last time; it didn't work. Let me see. I took a picture of my results because it took a while for the skin to change its color on the bananas, and let me see if I have those here. Maybe I put it on another computer or something, but I thought I had a picture of that. There it is. Okay, here we go. So I took a picture afterwards. Let's see if I can get that to work here. There we go. So there's the there are the bananas. This was like later on that evening, and those two bananas were the same. They were kind of a little overripe, and that was a problem too, I think. But this is the banana. I put tape over this, duct tape, so there would be clear lines where the light was shining and where it wasn't. And so I had duct tape on one end here and on the other end here, and then I shined light in the center. And then when it was all done, I took the tape off and I couldn't see any difference. So I said, "Oh, the experiment's a failure." And so I set these aside. And later on that evening, I looked at them, and this one here that I shined the light on turned dark all over the place, and in blotches. It was just really weird. And a real dark area here. I just was really confused as to what happened here, because I had tape over it. It shouldn't have done that. So I don't know why I did that. Maybe the tape, just the trauma, or the physical trauma to the skin of the banana, peeling the tape off or something caused it to do that. Anyway, that was a failure. So what I need to do now is repeat that experiment. Let's see if I can do it right this time. And what I did part of the experiment already today. And let me get my bananas here, and I'll explain to you what we're going to do. Got different bananas labeled differently here. Got 4 different ones. so this is what you do, right? If the experiment messed up, and you have ideas as to why the experiment messed up, then you try to change the experiment to make it work. So I've got all these bananas, and what I did is I took, instead of using tape to tape on the banana, I used this little elastic, which is a lot more gentle. And then I labeled each of them, which light I'm going to expose them to. This one, obviously, it's 8 o'clock here in eastern U.S., 8 p.m. There's no sun, so I had to do this one earlier. And I put this thing over it and just stuck it in the sun for 17 minutes. And that was early. That was at when the sun was almost at its zenith. So that was around 12:30 p.m. here. We're on daylight saving time, I think, aren't we? I don't know if we did we set the things back, but that's around when the sun is the highest. There were some high clouds and stuff like that, but those don't affect that much UV anyway. So I wanted to see if what that would do. And then I've got one for UVB, one for UVA, and one for UVC, which we're going to test. And we'll see if any of the different frequencies of light affect it or not. So I did this one earlier. Now I have lights, ambient light here, which I was going to turn down, and I probably should turn down the lights here a little bit, just so we can see what's going on with some of the other lights. But so I guess we'll do UVC first. And also, last time I didn't test UVB. I tested UVA and I tested UVC, but I didn't test UVB. So we'll test UVB also. I have a lamp here that is UVB. So yeah, let's do UVC first, and I will get my let me see if I can find my safety glasses. This happened last time too. All right, I don't know what the fuck happened to my safety glasses again. I lost them again. I can't believe this. This happened last time too. I couldn't find them. I found these old dusty pair. I don't know if they're going to work or not. Shit. My safety glasses, I know, block UV. And so now I got this other one I just found, and I don't know if it blocks UV or not. So I'm going to try again to find my... Hang on just a second here again. Jesus. Yeah, they were where they were supposed to be, but just hidden behind something in an unusual way. So, all right, so we found them. All right, so we'll do that. So I know these block anything, you know, above visible, pretty much. These safety glasses, so those will work. And I've got, again, I don't remember which one of these actually work. I've got 3 of these things. Let's see. Okay, that one didn't work. That one works. Okay. And this one I'm pretty sure does not work. Does it? No, it doesn't work. Okay, so I got one that works. So I'll take the UVC banana and put it over here. And somehow adjust this. This is just run by a few little batteries, so it doesn't make a lot of energy, right? Compared to the sun, you know, like I tested this other one. So what I want to do is, but it has a lot more energy per photon than the average light coming from the sun, or any other light I'm going to use here, because it's UVC. It's a shorter wavelength. And we talked about that, right? About it. The shorter the wavelengths means the higher the frequency, and the higher the frequency, the more energy per photon. So what I will do is, I've got a stopwatch around here somewhere. There we go. And I'll try to remember how many minutes, you know, I have a countdown timer, but I don't know what to do with that. So we'll just remember when we started here, and I'll just use a thing. So if I do it this way, that's too close. There, that's really close, but it's that'll work. All right, so that's what I'm going to do. I don't know if you can see that or not. Can you see that, what I'm doing there? Yeah, you can see it there. Here. Still see me? Still see that? Okay. So I've got this, I got the banana, the UVC banana. I lay that down right here. Now I get the UVC light. I will turn on the light and set it down right like that, very close to the banana, because it doesn't put out as many photons as some of the other lights that I have you know, here, because it's run on batteries. And we'll run it for 17 minutes, which I think should just totally fry that banana. But we'll see. And I've got that elastic wrapped around it, so that it should not go through, the UVC light should not go through that. UVC doesn't go through very much. It shouldn't, except for banana skin and human skin a little bit, you know. All right, so we'll do this here. I'll do it 17 minutes, which is way long time for this. There we go. All right, and it seems to be putting light all over the banana there. Can you see that? Yeah, you can see that, can't you? Yeah. I'm going to turn off this light here so it's a little bit more. I'll get this big light on. Oh yeah, look at that, that works. So that's counting down. So that's going. We're going to do that for 17 minutes, which is way long time. I don't even know if the batteries will hold out for that. The thing is, the instructions on the thing says that you should use it for 10 seconds or 20 seconds or something like that, which of course doesn't do anything at all. And while we do that, I want to look up this thing. This is the my UVB. So we're starting with C, B, A, and the sun, and we'll compare them all. This is it's what they call a reptile basking lamp that produces UVB. UVB is what humans and a lot of other creatures use to make vitamin D, and reptiles use it for something else I forget. But they absolutely need UVB light to survive. So when people take them out of the wild and capture them and put them in cages indoors, they die because they don't have the access to the UVB light from the sun. So this is called UVB 150 or PT 2189, and I looked it up, found the company online here, and I'll bring it up. Let's see here. All right. So, and I looked it up and I found it. This is the light I have. I'm pretty sure. 25 watts. I don't know. Doesn't see how many watts on here, but that looks kind of like what I have. So, and when I bought the thing, it had a little chart on the side of the package that had the actual frequency spectrum of the thing. But I go to the website here, and of course they don't have that. They're not showing that at all. So that kind of sucks. So I'll have to find that somewhere else, I guess. You'd think they would have that. Specs Explorer. Let's see. Care Guides Academy. Connect. Need help. Yeah, I want to find out what the specs are. Instruction manuals. Here we go. Maybe it's in there. Come on. All right. Instruction manuals. Trims. Lighting. Okay, here. We might even actually find this here. Wouldn't that be cool? Let's see. So we got PT 2189. Okay, I'll do it this way. Search for 2189. It's not in the goddamn thing. They don't have. They got every goddamn manual except for this one. Of course. You know? Fuck. Alright, let's see. Dome. Let's go by the name of the thing. Alright, let's go back. It's called the UVB 150 Reptile UVB 150. Okay? So. Shit. Okay, I'm having trouble with this goddamn thing. Opening another link so I can get back to the fucking page I started at. Please. Alright. Lighting. So what was it called again? UVB 150. Let's try searching for that on this stupid page here. UVB 150. UVB 150. 50. No, let's just search for 150. 150 watt. No. So they don't have the goddamn thing in here. It's just unbelievable. How can they not have that? Unbelievable. All right, let's see if Google is doing. I'm gonna put my mug back up here again and do a Google search for the thing again. PT 2189. All right. close. We're so close. There it is. Damn it. I think I found it. There. Oh, come on. Holy fuck. What do we got here? There. All right. No. Okay, well, let me put this up here and I'll show you what I've got going on here. Unbelievable. Alright, so I'm searching. Let me just show you what I'm doing here, just so you know. I typed in the model number of this lamp, and it's giving me all kinds of images here. And some of them show the spectrum here, but I can't get a big enough picture of it. This one shows it looks like it's really big, and I went to the goddamn site and it was a tiny little picture like this, you know. So alright, this one here. I don't know if, can you see that? Maybe I can zoom in on it or something. Alright, let me try going to this site, see what's there. Alright, I guess that's all we're going to get. Alright, so this is... So it's showing the spectrum here, and it's got wavelengths. I don't know if you can see that or not. Oh, my fucking light went off. I don't know how long ago that happened, so that kind of fucks up the experiment, doesn't it? Alright. So this is the spectrum of the UVB light, which is our next test, our next experiment. Maybe I can zoom in with this way. Can I do that? Can that zoom it in? That zooms it in a little bit. Oops. Alright, there's a little bit. Yeah, you can see that, can't you? Kinda? Alright. So, this is wavelength. God, I can't even really see that. Jesus Christ. Okay, 5. 7, 6. 540. I really can't even, it's too fucking blurry. Alright, let's go back to Google here and see if we can find one that has a better goddamn picture of the thing. Alright, I'm gonna do this in case, just in case. And I'll just try to find another picture of that thing. Probably would have been easier for me to go through all my shit and try to find the thing, but I don't think that one's going to be a good picture either. Okay, well, we don't have a lot of choices here, unfortunately. Okay, this one's a little bit more legible. I know what I'll do. I'm gonna take a screenshot of that. And I'll save it. Okay, I'm saving that to my pictures. Now I'll come over here and I will find that and these pictures. Okay, and then I will zoom in. Okay, we don't need to zoom in. We can just do it this way, I think. Okay, sorry this is kind of shitty. It's really scuff here, but that goddamn thing went off again. Okay, we're not. I don't know where you're gonna get 17 minutes out of that. It keeps going off on its own. So, all right. Now I got to figure out how to get OBS to put a picture in there. Media source. Okay, OBS is not cooperating at all. All right. Jesus Christ, what a fucking man. That was a pain in the fucking ass, man. All right. All right, we got Chatter out there. Hang on, Chatter. I want to get this done, and then we'll talk to you a little bit. I finally got this fucking thing up here. I want to talk about it now. All right, so we got all right, so this is this lamp. This is a UVB lamp. This is our next test. As soon as that one's done, that one should be done in a few minutes. I'm gonna run it a few minutes longer, I guess. I don't know, because it keeps shutting off, but I don't know how many minutes it was off. So, all right. So what I'm gonna do? There we go. All right. So this is what this bulb produces according to this source, which I have no idea if it's a good source or not. Looks right. Looks close. So the visible starts right about here, 700 nanometers, and it runs all the way up to about here, 400 nanometers, somewhere in here. So when I put that bulb in there and turn it on, we'll get some visible stuff here. It'll look kind of a pale white because it's got all these different colors. But then it also has near infrared, or I'm sorry, near UV, which would be UVA. That's right here. But it also has UVB, which is down here. And so that's the spectrum. So when we expose, but it doesn't have UVC. UVC is like 250 or something, or in below. So this bulb will not have UVC in it, but it'll have UVB. So we'll expose it to that, and then hopefully that will that'll give us at least some sort of an indication about what's going on. All right, so let's do chat here a little bit. Wait, let me yeah, we'll let that cook a little bit longer, and I'll do chat here. Hey, Big Ducky Snow, how are you? So Big Ducky Snow is in chat, and he says, let's see, rainbow, something rainbow. Not sure what that's about. He gave me a hug. So let me give Big Ducky Snow a hug back here. For those of you watching this on the VOD or are unfamiliar with what goes on with Twitch, on Twitch, it's, this is a live stream. Obviously, I'm just streaming this out there. But on Twitch, during the live stream, it has a facility here where the viewers can chat to me through a little chat thing, with text typing in. And so Big Ducky Snow, he's a friend of the channel here, and he has typed in, and he says, so he gave me a hug, a way of doing a virtual hug here. He says, "Have you been making out today, friend? What sort of experiment are you doing?" Yeah, yes, Stephen, I've been fine. I just started this stream at 8 o'clock, so we've been doing it about 40 minutes, and I've got 4 different bananas that we're doing. In case somebody else is just joining us, we've got 4 different bananas that we're going to expose light to, UV light to. And one of them I did earlier. I put it out in the sun for 17 minutes, and we'll see what happens to the skin of the banana that's exposed to the sun or to the UV light, different frequencies of UV light. So that's basically our experiment. And it says, perhaps you could answer in a whisper. Oh, all right, maybe I shouldn't read this out loud. Let me read this to myself. Okay, so he just says he's happy to be here and happy to join the stream, and said he needs to head out. So I don't know if he's still there or not. All right, so but for those of you who just joined, I explain what we're doing, kind of. Alright, so I guess this experiment is done. It keeps shutting off, so I don't think we got a full 17 minutes, but we got something on this UVC banana. So I'll put less than 17 on here for our time. So there's something less than 17 exposure to UVB on this banana. So we do that one. Okay, so now the next one I wanted to do was the UVB or C. Yeah, that was UVC. Now we're doing UVB with this lamp that we just looked at this spectrum of this lamp, so we know what it's being exposed to. Invisible light probably doesn't do anything to the banana, at least not very quickly or immediately. But But these higher frequencies or shorter wavelengths may do something, like the UVB may do something, and that's what we're going to test. So I'll take my UVB banana and put it over here. I've got a lamp here. There's an ordinary lamp, so I'm taking that out and I'm putting in this special lamp. so it works. Pretty close. But this one is 25 watts, it says. And looking at that chart there, it looks like maybe 5 of those watts, maybe, or in UVC, if that, or UVB rather, if that. They actually have a spec on here somewhere that says how many, you know, a little bit more details on it, but that's okay. We don't need all that. We'll run it for. Maybe I'll do this one for 10 minutes. So get it set up. Turn it on. Start my stopwatch. So there we did. I got the bin end of there. I'm shining the UVB light on it, and I'm gonna time it. But I think I'll only do 10 minutes on that one because it's a lot stronger. You know, overall, more photons. Each photon has less energy than this other one that I was doing. This UVC light here, right? UVC. Each photon has more energy on this, but on that one, each photon has less energy. But overall, there are a lot more photons. So I'll leave it on for maybe 10 minutes or something like that. So, all right, we do that, and now the next light I'm going to use is a UV UVA, right? That's the next one we'll do after this one, after we do UVB. And let me bring that up here. I can't hardly see what's going on here. I'm going to switch my glasses here because I think these are safe from that. UVB is not like UVC. It's not going to, and these stop UV anyway from the front. I just have a little bit on the side, so I'm not that worried about it. Plus, it's behind me. I designed this whole thing so it would be behind me. So, but I can't see the screen with those safety glasses on. All right. Well. All right. So, okay. Here's the Wikipedia article on ultraviolet light. Ultraviolet. And so they show a guy doing arc welding, which makes apparently UVB, I guess. Now they're talking about skin cancer and sunburns and all that. That's UVB, mostly. It says, for humans, suntan and sunburn are familiar effects of exposure of the skin to UV light, along with the increased risk of skin cancer. The amount of UV light produced by the sun means that the Earth would not be able to sustain life on dry land if most of that light were not filtered out by the atmosphere. More energetic, shorter wavelength extreme UV below 121 nanometers. Okay, so that's lower than that's a shorter wavelength than anything that we've got here. So it says extreme UV below 121 nanometers ionizes air so strongly that it is absorbed before it reaches the ground. It says, however, ultraviolet light, specifically UVB, is also responsible for the formation of vitamin D in most land vertebrates, including humans. The UV spectrum thus has effects both beneficial and detrimental to life. Okay. All right. They were talking about the atmosphere. Let's see if we can find that here. I'm sure there it is. So this is what it looks like. The UV A and B and C and all that. through the atmosphere. So along this side here is the altitude in kilometers. So 20, 40, 60, and then there's 80. So that's almost a little bit more, and you're in space. I guess it's officially in space up there. So UVA, almost all of it comes through. They're showing they're visually showing this as the width of the column here is symbolically representing the amount of that light that makes it through the atmosphere. You get that? So it comes through the atmosphere, and most UVA makes it all the way down to like the tops of mountains and stuff like that, except the really tall mountains. And then maybe, you know, half of it or something makes it to the ground. And in UVB, it gets filtered even higher up, and it gets filtered all the way down, and there's just a tiny bit of it that makes it through. And UVC gets blocked completely. So yeah, UVC does all kinds of crazy stuff. You know, you want to put that in your skin or anything. So that's and UVB can do stuff, bad stuff to you, right? Give you sunburn and all that too. But it also makes vitamin D. So and UVA, I don't know what that does to your skin anyway. Hurts your eyes if you put too much of it on your eyes. All right, so they're talking about that. Okay, this is the kind of light, the black light. That's UVA. That's the next one we're going to do. I've got a lamp similar to this, fluorescent lamp, and we'll expose this UVA banana to the UVA light and see what it does to the UVA banana. Fluorescent. Okay, so yeah. Has it been 10 minutes? No. Okay, so we've got 3 minutes left, 3 minutes and 10 seconds. And then I'll shut off that UVB light there in the background. And we may not be able to see the effects on the bananas in the amount of time that I'm on stream here. So maybe I can come back on later on tonight or tomorrow morning or something, or whenever it looks like there's the effect is happening, and then we can look at it. Okay, other black lights. Okay, so yeah, they're talking about just what the black light is. Now it says here that yeah, the old way they used to do it is they just make a regular incandescent lamp, you know, just the old-fashioned ones, you know, that heat up a wire inside and all that, and then they would let some of that go through. And oh yeah, I've got one like that. This one here is an ordinary light. Can't see that there. I don't know if you can see that. I shot it in there. Yeah, you can see that kind of, can't you? Yeah, so you can see inside there, kind of. I got another one here. Show you what those old ones are. This is kind of repeat about what we did last time, but it's. Alright. See that now? Yeah, I think you can see that. Oh shit, I gotta change my goddamn OBS here. Alright. Maybe from the side. Yeah, there we go. Here, let me focus my OBS or my camera. that up there. Let's see if I can get that in focus. There we go. Okay. Alright, now we can see in there. Look at that. So inside this thing, you can see it's got a little filament in there, just like an old lamp. And these in the leads that are going down here and to the base here, those leads bring electricity up to that filament. And if this was an ordinary bulb, you just have clear glass here, and that would glow really bright, just like a regular bulb. It'd be kind of an orangish tint to it that you wouldn't notice because your eyes adjust automatically. But that's what it would look like. But this one looks really blue and puts out a little bit of ultraviolet because they put this wood glass or some other type of filter over it to filter that out. Okay, it's been about 10 minutes now. So shut that off. And I'll put this back. I'm not gonna. I mean, I could turn this on. You want to see what this looks like since I got it out? Now, this bulb is actually pretty hot. This bulb is actually I can barely handle that bulb. It's really hot because it's not so efficient, right? It's making it's a fluorescent light. Let me adjust my focus here again. There we go. Because it's a fluorescent light. Fluorescent light makes UVA inside of it. It makes like 181 nanometers, or I think they got one spectral line at 181, another one at 254 or something like that. The mercury vapor inside of the fluorescent light, and then it hits a phosphor inside of the coating of the light, and then that phosphor fluoresces, and it fluoresces at a lower frequency, or a wider bandwidth, or wider wavelength, which would be that spectrum line that we showed you earlier for the UV bulb. Now this one is just incandescent heating. We talked about that. Black body, you heat it up, it makes splats. It splatters over the whole spectrum. That's what this does. But the filament inside there is splattering all from visible light all the way down to infrared. But they put a filter on it so that the very high part of it that goes into the ultraviolet actually leaks out, and some of the visible. So I'll just. There we go. So it's actually blue. It's a blue light. Oops. Oh wait, we don't want to put that on this banana. This banana's done. So it's. Yeah, you can see it's kind of fluorescing a little bit. I don't have anything that would fluoresce, but it's not. It doesn't do as good. It's not that good. Anyway, and that's hot. That was just on for a couple minutes, and it's too hot for me to handle. I gotta wait for it to cool down. Now, the next light I'm going to use though is a fluorescent light. Fluorescent UV light. Actually, all of the lights. Well, the first one was a mercury light, which is it's the same thing. It's fluorescent. It's a fluorescent light. These are all use fluorescents, but they're the first one actually doesn't use fluorescent. It uses the same idea as a fluorescent, but it doesn't actually have the actual phosphorescent material. But this is a UV light. You see that? You can see that, can't you? And this one is at 365 nanometers. I actually labeled it there. I figured it out one time and labeled it. So this would be for our UVA banana. Oh, I should write down the time that I did that other one, which was about 10. .30. You can't read. 10 minutes and 30 seconds. Right, this one is going to put out a lot more. So I don't know if you can see that. Yeah. Hey, there we go. That one's nice and blue. See it. That's a nice blue fluorescent light there. Purple, violet, or whatever color. So, let me find something that fluoresces here. Okay, that really fluoresces. See that? I don't know if you can see that. See how bright that is? And this is something that doesn't fluoresce very much. Invisible light, these look about the same. Here, I want to get close to this, to my regular light here. There we go. These are pretty much about the same of it reflecting visible light. But when I put them under here, the difference there. You see that? You see how that's different? And that's from phosphorescence. The one on the bottom here is just reflecting the visible light, and the UV isn't reacting to it at all. But this sheet of paper here is absorbing the UV and re-emitting it in a lower frequency or a longer wavelength in the visible spectrum, which makes it really bright. So that's how UV, that's how black lights work. Real quickly, anyway. All right, so now I'll take my UVA test banana and put it under there for, I don't know if I should do 10 minutes would work. I don't know. I think it'll be okay. All right, so we'll put that there. Pretty close, and we'll do that. This is a lower, longer wavelength. So I'll do this one 15 minutes, I guess, and we'll see what. All right, let's read a little bit more on what UV is doing. So this is the one we're using right now, just a black light, right? You've heard of black lights, right? So, so we will. Okay, long wavelength UVA radiation and little visible light. Yeah, it doesn't have all of the. You notice that all of these had a little bit of visible light on them, and that's just leaking. You know, light just leaking from, for various reasons, leaking into the visible spectrum, and that's actually desirable, I think, for in most cases, on lights that are just ordinary people are going to have access to. You're going to want that, unless you're a scientist and you know how to tell when the light's on and when it's not using other instruments. You probably want it to show some visible light when it's on. That way you won't accidentally turn it on without knowing it, Let's see, purple. Okay, so it says some lamps use the deep bluish purple woods glass. That's what I was explaining to you earlier. Which blocks almost all visible light with wavelengths longer than 400 nanometers. The purple glow given off by these tubes is not the ultraviolet itself, but visible purple light from mercury's 404 nanometer spectral line, which escapes being filtered out by the coating. Oh, okay. So, there you go. Other black lights use plain glass instead of the more expensive woods glass, so they appear light blue to the eye when operating. Okay, that says citation needed, so I don't know. Yeah, this is Wikipedia we're reading here. So, let's see. Incandescent black lights are also produced. Comma. Really? Incandescent black lights are also produced, comma, using a filter coating on the envelope of an incandescent bulb that absorbs visible light. Okay, that's what I was just talking about. They're kind of duplicating themselves here. Okay, this is kind of screwed up a little bit, but that's okay. Okay, black lights are used in applications which extraneous visible light must be minimized, mainly to observe fluorescence. That's what I was just demonstrating to you, the fluorescence of different material. The color glow that many substances give off when exposed to UV light. The one I demonstrated was just white, but yeah, some of them do different colors and stuff. Okay, UVA/UVB emitting bulbs are also sold for other special purposes such as tanning lamps and reptile husbandry. Citation needed. Why would you need a citation for that? That's obvious. Why? Why would you need a citation for that? Why are they saying citation needed? Okay. Shortwave ultraviolet lamps. So that's what we did earlier. Shortwave UV lamps are made using a fluorescent lamp tube, with no phosphor coating. Right, that's what we were doing earlier. Composed of fused quartz and Vicor. I don't know what that is. Oh, it's a brand name. Okay, just a type of glass. Since ordinary glass absorbs UVC. Which is true. Yeah, that's true. Yeah, ordinary glass absorbs all UV, most UV. Very, very little UV gets through lights, through like a window, an ordinary window, or just any kind of glass, glass, normal soda glass they call it. Okay, these lamps emit ultraviolet light with two peaks. In the UVC band at 253.7 and 185 nanometer due to the mercury within the lamp, as well as some visible light. Now the ones I have, I think, are filtering out the 185. These little ones that I was doing. This thing. I think it's filtering out the 185. I'm not sure. Okay, from 85% to 90% of the UV produced by these lamps is at 253.7. Okay, well, okay, so 185. So quartz tube passes the 254 nanometer radiation, but blocks the 185 wavelength. Such tubes have 2 or 3 times the UVC power of a regular fluorescent lamp tube. 2 or 3 times. And now, see, they should put a citation on that. How, if I was doing this, I'd put a citation right there after that sentence. All right, these low pressure lamps have a typical efficiency of approximately 30 to 40%, meaning that for every 100 watts of electricity, they produce approximately 30 to 40 watts of total UV output. Okay, they also emit a bluish white visible light due to mercury's other spectral lines. So they're kind of repeating. This is This happens in Wikipedia. You know, you get several guys getting in there and editing the thing, and it ends up repeating and stuff. So I don't know. Here, incandescent. They've mentioned incandescent black lights twice already, and now they've got another whole section on it. So, okay, ultraviolet LEDs. Oh yeah, I forgot that. I think we tested with ultraviolet LEDs last time, but I'm not going to do that because the one I'm using right there right now is at 365. Let's see. Let's see if they say that up here. No, they don't even say. It's 365. LED black lights are at 395. Typically, the ones that I've found so far. But apparently, they've been able to make some that are at the 365 now. But I don't know if they're available yet. I'll just read this here. Light emitting diodes can be manufactured to emit radiation in the ultraviolet range. 2019, following significant advances over the preceding 5 years, UVA LEDs of 365 nanometers and longer wavelengths were available with efficiencies of 50% at 1 watt output. Currently, the most common types of UV LEDs are in the 395 nanometer and 365 nanometer wavelengths, both of which are in the UVA spectrum. The rated wavelength is the peak wavelength that the LEDs put out, but light at both higher and lower wavelengths are present. And they said citation needed on that, which is why. Obviously, is maybe higher. Maybe they're questioning whether it puts out higher. It obviously puts out lower wavelengths because you can see it, right? The cheaper, more common 395, yeah, that's the kind that I have, are much closer to the visible spectrum and give off a purple color. The UV LEDs deeper into the spectrum do not emit as much visible light. LEDs are used for applications such as UV curing applications, charging glow-in-the-dark objects, such as paintings or toys, and lights for detecting counterfeit money and bodily fluids. UV LEDs are also used in the digital print applications in inert UV curing environments. Power densities approaching 3 watts per cubic centimeter, per square centimeter, are now possible, coupled with recent developments by photo initiator and resin formulators, whatever that is, makes the expansion of LED cured UV materials likely. And another citation. Somebody didn't like this article or something. They just put citation. All right, developing rapidly but may require testing. I don't know what they're talking about there. Yeah, you can. We did that on the other one. I used various UV lights to charge glow-in-the-dark material. Okay, so we're over 10 minutes here. All right, so that one's done. That's UVC. We did it 10 minutes. 10 minutes and 30 seconds. There, 10 minutes and 30 seconds. So we've got all these different bananas here that we've exposed to UV. Here, I'll show you that right now since I got that going. Find it. Here it is. See, here's some glow-in-the-dark material that I've had in an envelope for a few days, so it shouldn't have any glow-in-the-dark going on with it. shut off. I'll shut off all that light. I'll shut off this light too. Cover that up. There we go. So this is glow in the dark material, and it's not really glowing in the dark very much. You can see, right? That's not glowing in the dark too much. But when I put it under here, put my hand on top of it. That's always fun to do. then we get this. See? Isn't that cool? So, let me cover this up. There we go. There. So that was UVA doing that. And it turns out this stuff, I did a little bit more research on it, and this strontium that is used to make these things glow in the dark is most susceptible, or most reactive, or most amenable to absorbing UVA. So that was something I learned. Alright, let me turn the lights back on so I don't bump myself. Alright. Now let me shut this off. Alright. So we did our experiments here. So I can't tell. The UVC is the one that we were testing, right, to see if it would actually change, and I don't. It looks like it might be. It's changing a little bit here. Can you tell that? I don't know. This is the one that did the sun. So I don't think it's I don't think we're going to see a change yet. Let me just. I don't want to. See a difference there? No. All right, so I'm just going to leave that on there. I don't think we're going to see a difference right away. I think it's going to take a few hours. The one we had in the sun, I guess I should be able to see that one by now, but it's not. Oh, shit. Sorry about that. All right. So that one, see, it doesn't. There's no difference in there, you know. The sun didn't do anything to this banana. That was 9 hours ago. Over 9 hours ago, and I can't see any difference at all in that under there. So that would indicate, that would seem to indicate, if that little chart was correct that we had there. Let me bring that back up here. So I had it on, basically on the ground here in the sun, and so it was getting UVA and getting a little teeny bit of UVB, but no UVC on the banana, and it didn't seem to have any effect. And now this UVC, I mean, if you can compare these things, look at these three bananas here, UVA, UVB, and UVC. You can see, well, the UVA was the most recent, right? So, but it does look like there is, you know, this UVC one has got more stuff going on with it so far, right? A little bit. So, all right, I'll set these aside somewhere. Try not to bang them up too much. We'll just put them over here, right? We don't have any lights anymore. A, B, C, and the sun. Okay. So we'll just let it sit there for a little bit. Maybe I'll do a long stream. And we'll just test them at the end of the stream. And get people to stick around to the end of the stream because they're curious. Not. All right, let's see. So, yeah. So the one in the sun was was basically getting the same thing that we did with UVA, right? And maybe a little bit of UVB, but not very much UVB. So I'll be curious to see what happens with those bananas. And here's something we can figure out, right? Since the one was put out in the sun for 17 minutes, and that was 9 hours ago, and we can see no detectable change at all. This is what it was exposed to. So UVA probably is not going to affect it at all. And there's a little bit of UVB, so maybe the UVB will affect it. We don't know. But UVC, it didn't get any, the one that was in the sun. So maybe that's the thing. So we'll see. We'll see what happens there with that. I don't think there's anything else in here. Curious about when people are doing welding, what that does. Harmful effects, skin damage, all this stuff. Yeah, look at this. Look what happened here. No, I'm not gonna. This. Let's see. Danger, UV radiation. Eye damage. Yeah, they're talking about all kinds of stuff. Yeah, it does. It damages stuff. It damages polymers too. Let me put that up here. Talking about UV degradation. If you have something made of plastic that you want to put in out in the sun, you got to make sure it's been designed so that it won't degrade due to the ultraviolet radiation that comes from the sun, UVA and a little bit of UVB. Let's see what it says about that here actually. UV degradation is one form of polymer degradation that affects plastics exposed to sunlight. Let's see here. UV. Okay, it's talking about photooxidation. Okay, interesting. The problem appears as discoloration or fading, cracking, loss of strength, or disintegration. The effects of attack increase. What did you say? The effects increase with exposure time and sunlight intensity. The addition of UV absorbers inhibits the effect. Sensitive polymers include thermoplastics and specialty fibers like aramids. Aramid fibers, short for aromatic polyamide. Heat-resistant, strong synthetic fibers. UV absorption leads to chain degradation and loss of strength at sensitive points in the chain structure. Okay, let's get kind of into the weeds there on the chemical stuff. Oh, here they talk about the applications of the different wavelengths. This is kind of interesting. So way up here on the high end is bug zappers. Flies are most attracted to light at 365. And 300 to 365 is curing of polymers and printer inks. 300 to 320, light therapy and medicine. 280 to 400, medical imaging of cells. Okay. 270 to 360 nanometer protein analysis, DNA sequencing, drug discovery. 200 to 400 nanometer. Forensic analysis, drug detection. 240 to 280. Disinfection. Decontamination of surfaces and water. UV absorption has a peak at 260 nanometers. Germicidal lamps, that's what they were just talking about, right? 230 to 400. Optical sensors, various instrumentation. 230 to 365 is UV ID, label tracking, barcodes. I mean, you could, oh, now here's one really short wavelength, 30. That's X-ray, isn't it? Isn't 30 X-rays? Photoionization, ultraviolet photoelectron spectroscopy, standard integrated circuit manufacture by photolithography. I think they're using X-rays now to make integrated circuits, aren't they? I mean, they have to be, right? Let's see, extreme ultraviolet lithography. Now, X-rays are I'm going to look up X-ray here. Let me look that up here real quick. Okay, I found the article on X-rays, so I'll put that up here. Now these would be shorter wavelengths or higher frequency above ultraviolet, the stuff that we were working with today. Now they say X-ray wavelengths are shorter than those of ultraviolet rays. Where have we heard that before? And longer than those of gamma rays. There is no universally accepted strict definition of the bounds of the X-ray band. And the reason why they don't have a firm definition is because different areas of science classify it differently. If it's experiments that people do in the lab and stuff like that, then they go by how the X-ray is created, because they can. But if they're astronomers, they don't know for sure, right? They just detect this X-ray. They didn't create it themselves. They don't know how it's created, so they use like an arbitrary range. So there's no set amount. But it says roughly X-rays have a wavelength ranging from 10 nanometers to 10 picometers. So 10 pico is 10 picometers. That's 1,000 times shorter wavelength than 10 nanometers. So what we were working with is like the highest, or the shortest wavelength we were working with today was 254 approximately, or 285. Maybe there's a little bit of 285 coming out of those UVC lamps. But, I'm sorry, 185 coming out of those UVC lamps. But these are much shorter. X-rays are like 10 nanometers, much smaller than that. But this over here, see, they're talking about 10 still being UV, right? Extreme ultraviolet, they're saying 10 to 121, but so that's like X-ray. Entirely ionizing radiation, by some definitions, completely absorbed by the atmosphere. UVC, yeah. But X-rays are much shorter. Can penetrate many solid substances such as construction material and living tissue. So X-ray radiography is widely used in medical diagnostics. Checking for broken bones and material science. Yeah, that's what X-rays do. Explains medical imaging and X-rays. You want to watch this little video, 10 minutes? I don't know if I can. We got a little video on X-rays here. Oh, this is an old thing. Let's see here. Yeah, this has got to be Twitch safe, right? They're not going to show boobies in a old 1950s thing. I'm going to scan it anyway just to make sure. Okay. I'm clicking around in here and I don't see anything. I don't want to sit here and take 9 minutes to. All right, so we'll watch that little video then. Can you see that?
Late in 1895,
Is it making
in a
noise?
little university laboratory in Bavaria, Professor Wilhelm Conrad Röntgen first noticed the strange effect which led to the announcement of his discovery of X-ray. And although the news was received by the public with a mixture of disbelief and apprehension, doctors immediately saw the possibilities of the mysterious new rays and began to use them. It was not until 1913, however, that their use became certain and reliable. In that year, the hot cathode X-ray tube was introduced by Dr. William D. Coolidge of the General Electric Research Laboratory, the man who had already developed the all-important ductile tungsten lamp filament, and who now holds one of the world's few honorary degrees of Doctor of Medicine. In speaking of X-rays, therefore, it is a privilege to be able to present Dr. Coolidge himself.
For a long time, after X-rays were discovered and used, they remained a mystery even to the scientist. That is how they got their name, X for the unknown. Today, however, we know that X-rays are a form of radiation belonging to the same family as light, heat, and radio waves. We know also that X-rays are produced whenever a solid target is struck by a high-speed stream of electrons, those same little negatively charged particles of electricity which make our radio tubes work. In early X-ray tubes, the electrons necessary to produce the X radiation were released by first breaking down a small amount of air or other gas in the partially evacuated tube with high voltage applied between the terminals. Operation depended upon the amount of gas within the tube, and since this was variable, the tube was unreliable. In the present day hot cathode X-ray tube, of which this is one of several different types, there is a high vacuum, and the production of electrons depends only on the size and temperature of an incandescent tungsten filament with a cup-shaped structure surrounding it. This particular tube has two filaments, either of which may be used. The swarm of electrons, which is liberated or boiled off from the white-hot filament, is speeded up to a very high velocity by high voltage applied between the negative electrode or cathode, which carries the filament, and the positive electrode or anode, which is called the target. The electron stream is focused to a very small spot on the target by the cup-shaped cathode structure. It seems that the electron stream striking the target at terrific velocity is stopped so violently that the electromagnetic radiation known as X-rays is produced. The efficiency of X-ray production is very low, and most of the energy of the electron stream goes to heat the target. This heating effect of the electrons may be likened to the flame of a blowtorch striking a metal plate, while the light coming from the heated spot on the metal plate target corresponds to X-rays coming from the focal spot on the target of the X-ray tube. As a matter of fact, X-rays are like ordinary light, except that they are of very much shorter wavelength and are therefore invisible. Although X-rays themselves cannot be seen, their effects can fortunately be made visible. Photographic film in general is sensitive to X-rays, and a special type of it is used to record their presence. Recording of X-ray images on film is called radiography, and the finished films are known as radiographs. X-rays also have the power to make certain chemicals fluoresce, that is, give off visible light. A piece of special cardboard coated with one of these chemicals constitutes the so-called fluoroscopic screen. The use of such a screen to reveal an X-ray image is known as fluoroscopy. It has the advantage over radiography of enabling us to visualize internal structures in motion. Besides being of much shorter wavelength, X-rays also differ from light rays in that they cannot be focused in a camera. So ordinary photographic procedure cannot be employed. Instead, we use a shadow technique. If I now turn on this small spotlight and place my hand in its beam, I can cast a shadow of my hand on a white card. Now, if instead of the spotlight I use an X-ray tube such as there is in this little portable X-ray unit, and if instead of the white card I use a film in a light-tight holder, I can cast an X-ray shadow of my hand, which on the developed film looks like this. Note, however, that instead of a solid silhouette shadow, as with light, the X-rays produce a shadow which shows a distinction between the bones and the flesh. In other words, X-rays pass through some substances more easily than through others, and the details of the image depend upon the amount of X-ray getting through the different substances which make up the object. It is this ability of X-rays to differentiate between types of substances which gives the rays their great diagnostic value. It seems both incredible and paradoxical that rays which are themselves invisible can reveal objects which are otherwise also invisible. But that is exactly what X-rays can do. It is then no wonder that X-rays have, in less than half a century after their discovery, become so useful in medicine and industry.
Alright. Okay, so I wanted to look up fluorescence.
Okay, so I wanted to look up fluorescence.
Shut off my monitor. So I found the article on fluorescence, think there's an image. Alright. It says fluorescence is one of two kinds of emission of light by a substance that has absorbed light or other electromagnetic radiation. Fluorescence involves no change in electron spin, multiplicity, and generally it immediately follows absorptions. Phosphorescence involves spin change and is delayed. Okay. I wonder how okay, so it's, I wonder how reflection is. I guess the difference in fluorescence is that it changes the wavelength. Absorbed light or fluorescence involves no change in electron spin multiplicity and generally is immediately follows absorption. Fluorescence is a form of luminescence. In most cases, the emitted light has a longer wavelength and therefore a lower photon energy. So the difference, I guess, between fluorescence and reflection is that reflection doesn't change the wavelength either. Right? If light is reflected off of a material, so like if you had a red piece of paper and you put it in the sun, it looks red. That's because the sun is emitting wavelengths in all different light in all different wavelengths, but the material only reflects the red, and that's why the material looks red or yellow or whatever color it happens to be. But fluorescence involves changing the wavelength of the light that comes back from it. A perceptible example of fluorescence occurs when the absorbed radiation is in the ultraviolet region. Right, we were just doing that, right? Which makes it kind of more dramatic. Talk about different applications, history, physical principles, mechanism. Fluorescence occurs when an excited molecule, atom, or nanostructure relaxes to a lower energy state, usually the ground state, through emission of a photon without a change in electron spin. When the initial and final states have different multiplicity different spin, the phenomenon is termed phosphorescence. I haven't heard them use that before. Maybe they're changing the name from spin to multiplicity. So it's less confusing. Like they changed the name of force. They used to call it the 4 fundamental forces. Now they're calling it 4 fundamental interactions. Because it wasn't an accurate description of what was going on. The ground state of most molecules is a singlet state, denoted as S sub 0. Is that what this is? Okay. Okay. Therefore, most commonly, fluorescence occurs from the first singlet excited state, S1. Okay, so it's just one step up. Quantum yield. Oh God, look at this. This is really getting into some detail here. Lifetime. Non-radiative transition. Fluorescence. Oh, look at that. Jablonski diagram describes most of the relaxation mechanisms for excited state molecules. The diagram alongside shows how fluorescence occurs due to the relaxation of certain excited electrons of a molecule. That's what we're just looking at. Huh. Strongly fluorescent pigments often have an unusual appearance, which is often described colloquially as neon color. Originally day glow in the 1960s and early 70s. Day glow. This phenomenon was termed Farbenglunkt. I don't know what that is. Is generally thought to be related to high brightness of the color related to what it would be as a component of white. Fluorescence shifts energy in the incident illumination from shorter wavelengths to longer, and thus can make the fluorescent color appear brighter, more saturated than it would possibly be by reflection alone. There you go. So that's kind of cool. Okay, so it's I'm gonna look up reflection. They don't have a link to reflection, oddly enough, in here. Let me get there. Coral snakes, or just coral. What is that? Oh, it's just coral under the water, I guess. Kind of weird. All right, so I'm going to look up the word reflection in Wikipedia to see what it says about that. Okay, I found the article. Looks Twitch safe, so... Alright, so they're talking about reflection. Is the change in direction of a wavefront at an interface between two different media so that the wavefront returns to the medium from which it originated. Alright. Oh, this is really general. This is talking about acoustical reflection too. Specular reflection means that it's at a specific angle. And diffuse reflection is just ordinary, like like this diffuse anything is not a mirror, basically. Now, does it say what? Oh, here it is. Mechanism. In classical electrodynamics, light is considered as an electromagnetic wave, which is described by Maxwell's equations. Light waves incident on a material induce small oscillations of polarization in individual atoms, or oscillation of electrons in metals, causing each particle to radiate a small secondary wave in all directions, like a dipole antenna. All these waves add up to give specular reflection and refraction according to Fresnel principle. Okay, so it's okay, so it's basically it's not making the electron go to a higher state. It's wiggling the electron, and then the electron being wiggled emits the same frequency that it's being wiggled at immediately. Interesting. Okay. So yeah, that's different. That's different than fluorescence. So that's kind of the main difference, right? It's always going to be the same frequency that's being wiggled at. Well, that makes sense. When light strikes the surface of a non-metallic material, it bounces off in all directions due to multiple reflections by the microscopic irregularities inside the material. the grain boundaries of a polycrystalline material, or the cell or fiber boundaries of an organic material. And by its surface it is rough, if it is rough. Thus an image is not formed. This is called diffuse reflection. The exact form of the reflection depends on the structure of the material. One common model for diffuse reflection is Lambertian reflection, in which the light is reflected with equal luminance in photometry, or radiance in radiometry, in all directions, as defined by Lambert's cosine law. Okay. So that's getting into the weeds a little bit. But that's the main difference, between reflection and fluorescence, is that the in reflection, the wave is hitting the electrons in the material, and the electrons wiggle from the wave, the electromagnetic wave that hits it, and they emit the same exact frequency because they're wiggling in just the frequency with what they're beginning hit with. And fluorescence, it actually puts the electrons into a higher energy state, and then when the electron falls down, it emits electromagnetic radiation. But because it's not just being wiggled at that frequency, when it falls down, it emits the light at a different frequency, usually lower frequency. And then phosphorescence means that it doesn't fall down right away. It stays in the high state for a while, and then falls down. Sometime later. And the way that they determine that is by the electron spin. If the electron spin changes, it's been long enough, I guess, for the electron spin to change, then they call it phosphorescence. Phosphorescence. Which is what we were just playing with. Remember, I just did that image in my hand on that phosphorescence material. Alright, so let's see if these things have changed yet. The UVC one, shit, I just screwed up my... I just dropped the one from the sun, so that's going to have bruises on it. This is the UVC one. Let me turn the light back on. So how long has it been? An hour and a half? Something like that? Well, I don't see any difference from the thing. I'm going to scoot this off here, so I know what I'll do. I'll put a little mark on it where this was, just so I can tell for myself. Which I probably won't be able to see after it changes. But alright, so I'll scoot this up. So this is my UVC banana. I'm taking off the little elastic thing. Can you see a difference there? I can't see anything. So it was right here is where it should be darker on either side of that. I don't see it. Huh. Right, so we may have to wait. We may have to wait longer time than for that. Let me look at the one from the sun. Now, this one was a long time ago, right? So this was 10 hours ago. See what this one looks like. See, this is the one that was out in the sun for 17 minutes. And I don't see any difference in that either. Huh. All right, well. All right, well, I'll just leave them over here then. And check on them tomorrow morning or something, or I don't know. Whenever I see that there's an actual difference showing up, then I'll do a stream and we'll look at it. So we might have a surprise stream here sometime in the early morning or something, or whenever I'm awake and I happen to see that. All right. What else can I do here? I guess that's it. I've been out here for 2 hours. And we didn't get the results of our experiment. We did the experiment, but we didn't get the results. So, you know what I can do? I just realized something. I can find somebody, because somebody in YouTube has done this, right? Somebody out there has done this already, right? Somewhere. So what I'll do, type UVC, banana, UVC banana test videos. Oh, this is green banana. They use green bananas. I don't think it makes a difference. All right. All right. So I'm gonna have to check these videos out here to make sure they're Twitch safe. UVC banana test. I'll just go to. Jesus Christ! Why did that not fucking work, man? God, UVB banana. Oh, actually I should say UVC, not UVB. Maybe that's why it's not giving me what I want. And of course, YouTube doing their typical shitty search results here. God, unbelievable. Have you ever try to do a search on YouTube? Their search facility is just is the worst. It's worse than any search anywhere on the internet anywhere. Okay, here we go. I found some. Okay, here's a 3-minute video. All right. I gotta watch the video before I can play. Before I can play it here, right? Because of Twitch. I don't know what the guy's saying. I guess it doesn't matter. So this is a guy basically doing the same experiment I did. It looks like he's doing UV. I'm scanning this video just to make sure. Oh shit. I can't believe this. I can't believe fucking YouTube did this to me. I searched, okay, this is what I did. I just searched for the videos, right, for this stuff. And I clicked Creative Commons only, so I can play the goddamn thing on the stream. Gave me a list of videos. I found this video, and I'm scanning this video. As I'm scanning it, I decided to look at the description, and it's not a Creative Commons video. So YouTube fucked up that part of it too. Unbelievable. I can't believe that they, how can this is a huge, trillion-dollar company. Been out there for a long time. They've got the best engineers in the fucking world, and they can't do a goddamn search, This is unbelievable. Unbelievable. I'm flabbergasted. All right. So I'm going to have to fuck around with this a little bit more. No. They're giving me nothing here. They're giving me no results. No. YouTube, your search sucks. And Google, I can find shit on, which is just absolutely bizarre. It's the same goddamn company. Why doesn't YouTube just use Google search for their videos, All right, so this one gives me lots. I do a Google search. It gives me lots of different stuff here, but I can't sort by Creative Commons on the Google results. Let's see. No. Well, I don't think we're going to be able to do this. I guess what I'll do is when I get the results from my test, I'll put it up. I'll put my results up there as a YouTube, and I'll put it out there as Creative Commons so other people can use it. And I'll try to type in words that will make them find it in the. That's Facebook. I don't want to go there. Let's see, YouTube. UVC versus banana tests. Let's see here. Yeah, maybe I should do that. I should just take this stream when I get the results, and edit it down and put it up on YouTube, so there'll be one up there that's Creative Commons. Huh. I wonder if I put Creative Commons in here. Creative Commons. Bananas can detect invisible light, ? Okay, this one I think we can play. Maybe.
When they're dehydrated, Pedialyte is good for very long. Doesn't have to be good. Doesn't this? It depends. Yep, it depends. If you're feeling super hot or super not, it... Alright, it's time to turn a banana. More specifically, time to find out if the banana...
Oh no, this is...
UVC light. If it is, it would be a single UVC detector for everyone.
No.
The sample protect.
Handheld DNA eraser. See, if I do a search, it's like here. Let me show you what I'm doing here. I went to YouTube, right, and searched, and they fucked it up. I can't, if I type in UVC and banana on YouTube, and then click Creative Commons, I don't get any results. or I did get some results, but when I go to them, they're not actually Creative Commons. So I go to Google, which has a better search facility, but I don't know if it's Creative Commons or not. I type in Creative Commons as an extra thing, and it gives me every video that has used Creative Commons contents in the video, which ain't right. That isn't what I want. Now they used to have a tool here on Google where you could say Creative Commons, give me, Creative Commons results, and they got rid of that for some reason. So apparently Google doesn't like Creative Commons or something. Although they probably use it all the time themselves anyway. Let's see. Narrow your results. This language, this duration, posting date, this quality, site or domain, subtitles. So why did they get rid of that, Alright, I guess we're screwed. We'll have to make up our own video when the bananas are done cooking. Which might be a few hours, I don't know. Alright, I guess I'll end stream. So I'll do a surprise stream sometime when when I start seeing results of on those bananas, and then we'll do that. I'll show you if there are results. So okay, all right, everybody. Then keep your if you're not subscribed, if you're not following me on Twitch, get over to Twitch and hit the follow button, and then you'll get notified, and then tell it that you want notifications. There are about 12 dozen different places that you can say whether or not you want notifications or not. I have no idea which combination of those work what way, but I guess you need to go to all of them and tell them that you want notifications in every single place that you can find in every single menu somewhere. And then you'll get notified when I do my surprise stream. So, all right, everybody take care. Make sure you wear your N95 mask when you're in public so you don't kill people, old people like me, If you're a young person, maybe it won't affect you. It'll just make you sick and make you die earlier. But if you get infected with COVID, and then you infect somebody else, and then they go home to their parents and kill their dad or their granddad or something. So wear your N95 mask if you care about people. Of course, if you don't care about people, if you only care about yourself, then do what you want. But if you care about other people, then please wear your N95 mask. And wear your seatbelt too, for your own good. All right, everybody. Take care. Bye.